Okay, let's get started. We're pleased to welcome Professor Annmarie Carlton as our speaker today. Annmarie Carlton is our speaker today. Annmarie is a guest speaker in our newly formed ACORD seminar series. She was one of the original members of the ACORD Science Committee, and we're grateful for her contributions toward making ACORD a reality and for its continued success. Annmarie is originally from Sayreville, New Jersey, the home of rock singer Bon Jovi, who by the way, was an altar boy alongside Annmarie's brother. She attended Rutgers University for her bachelor's, master's, and PhD. After receiving her PhD, she worked as a scientist at the NOAA Air Resources Laboratory and the APA in Research Triangle Park, North Carolina. She joined the Faculty of Environmental Sciences at Rutgers University in 2010. Her research focuses on secondary organic aerosols and how the combined interactions of SOA, water, and photochemistry influence local climate. She also teaches classes and supervises graduate and undergraduate students at Rutgers. Annmarie was the lead investigator for the summer 2013 Southern Oxidants and Aerosol Study, SOAS. She oversaw the activities at the ground site near Brent, Alabama, which was one of the largest measurement campaigns ever assembled. She has received numerous awards from the EPA and is a member of several scientific organizations, including AGU and AAAR. Her talk today is entitled Aerosol Water, Now You See It, Now You Don't.
Thank you. That was very thorough. So thank you everyone for coming on a storm day. I know you want to be outside watching it probably. Getting to be involved with NCAR put my career on a completely different trajectory, and NCAR will always hold a special place for me. Aerosol water, now you see it, now you don't. No one in this room really needs to be reminded of why we care about atmospheric aerosol, but I like to do it anyway. On the top panel, I'm showing 3 photographs. Whenever you do a Google image search for air pollution, the image that comes back to you is typically for a time and location when the concentration of atmospheric particles was very high, and that's because they efficiently scatter in the visible part of the spectrum, and so we see them. In the top row, I love the analog pointer. In the top row, this is actually a daytime photograph in Beijing, and those orange rectangles are the reflection of sunlight off of window panes. And this is India, and for all of the discussion in the popular media about the developing world, high particle concentrations and the air quality and health impacts remain a domestic issue, and this is a photograph of LA from 2 summers ago. Because particles scatter radiation in the visible part of the spectrum, they impact visibility. Believe it or not, we have beautiful national parks in the eastern US also. Because they scatter radiation directly and because they can serve as cloud condensation nuclei, particles can form clouds and impact climate. And one thing that I really like studying is biosphere-atmosphere interactions. I like thinking that plants and trees in the forest are actually talking with the atmosphere, and they communicate through particles. And oh yeah, particle pollution causes cancer. And recently in the literature, high particle mass concentrations have been linked to autism and other neurological disorders. So our community has known for quite some time that biogenic emissions can interact with emissions from human activity to form ozone, even resulting in non-attainment of national ambient air quality standards. And Atlanta, Georgia is a classic example of this. And the time period, I actually worked for Region 2 of the EPA at the time, when there was a technology transfer from the scientific community to the regulatory community, that this process was going on. And that translation, I think, happened during the Southern Oxidants study. And so I was really influenced by that. And later on, I went back to EPA and I made the Southern Oxidant and Aerosol study. So we just added that A. My son Reese was reading The Hungry Caterpillar at the time, and so I was really influenced by pointillism art, and that's why the logo looks like that. And so the idea that has been brewing in our community for quite some time is that these same biogenic emissions can interact with those same emissions from human activity to form particles. And so this anthropogenic pollution can facilitate formation of particles with modern carbon, this biogenic secondary organic aerosol. And regulators have traditionally thought of that as part of the natural background and not as a part of pollution targets. And I wanted to change that paradigm. So the way that we understand formation of particles in the atmosphere, the way that we typically describe it in models is something like this. There are emissions of volatile organic compounds. Some of our favorites are isoprene, monoterpenes, sesquiterpenes. And in the gas phase, they can react with a variety of oxidants. And some fraction of the oxidation products decrease in volatility. And because we're very creative, we call them semi-volatile organic compounds. Traditionally, we use an ODA model with 2 products, but it doesn't matter. You can use as many as you want. And then in general chemistry, or chemistry in the 6th grade, we learn like dissolves into like. So these organic gases will partition to and dissolve into a pre-existing organic aerosol matrix, should it be there. And then the burden of particles in the atmosphere increases. But the thing is, the majority of organic compounds in the atmosphere on their way to CO2 are actually small water-soluble organic compounds. And we've known this for quite some time. So I don't think of 1996 as a long time ago, but my students think that that was incredibly long time ago. And so this idea that I've been thinking about is that actually the majority of organic carbon in the atmosphere are these small polar compounds, water-soluble organic compounds. And because like dissolves into like, should an organic compound have polarity, it will dissolve into a polar solvent, and liquid water is a ubiquitous and abundant polar solvent, and I'm going to try to convince you of that today. So here, what I'm showing, I used to work for NOAA until there was a hostile takeover of our group by EPA, and I worked there as a CMAQ model developer. And what I'm showing here are CMAQ results, a map of the modeling domain, and then the hotter the color, the higher the concentration. Here, these are gas phase water-soluble organic gases that have been shown in laboratory experiments to make secondary organic aerosol. And they can partition into particle phase liquid water. And on this side, what I'm showing are gas phase semi-volatile organic compounds that have been shown in laboratory experiments to make SOA. And they can partition into this organic aerosol matrix. And so if you just look from a big picture point of view and you want to understand the chemical potential of this pathway, the chemical potential of this pathway, it seems at first glance that this chemical potential is higher. So I was really interested and personally motivated to understand that idea. So I wanted to go to one location that would experience a range of conditions, and I'm interested in this process, semi-volatile organic gases partitioning to particles, water-soluble organic gases partitioning to particles. And so I wanted to go to a place with lots of aerosol water. I wanted to go to a place with lots of water-soluble organic gases, and I wanted to go to a place with lots of semi-volatile organic compounds. And so that was my own personal motivating science behind the Southern Oxidant and Aerosol studies. So just to give you a big picture, I see some people here who were here at the campaign. We had our main ground site here in Brent, Alabama. This is the edge of Talladega National Forest. And if you look really closely, you can see me in the shed maybe. I spent a lot of time there. Then we also had a flux tower nearby inside the forest canopy. This is John Mack's airplane, and this is Paul Shepson's airplane. And we would get very excited when they would fly over the field site. But Paul would constantly text me because he knew I hated it. And that was a big mistake letting him know I hated it, because that only encouraged him to text me more, sent from my iPad. This is the NCAR C-130. And so the bulk of the funding for the SOAS campaign came through an OFAP request. This is NOAA's P3. This is another smaller site that we had in Rocky Mountain National Park. If Peter McMurray's SEEVE study was here in the 90s. And then Research Triangle Park EPA also had a small study. So how did we get the community to buy into this, and why did we pick the Southeast US? And so in our white paper for the SOAS campaign, these are the 3 figures. So this first figure is made by EPA from NOAA data, and it's showing temperature anomalies over the last 100 years. And over the last 100 years, most of the world and most of the US has been getting hotter, and that's what these hotter colors indicate. But there's this warming hole in the Southeast US. And even if you look at the cover of the most recent IPCC, there's still a hole there. And then on here, this is a great paper by EPA, where they were looking at the controllable fraction of biogenic secondary organic aerosol. They did a series of model runs. They removed controllable anthropogenic pollution and looked at how biogenic SOA mass concentrations went down. And then lastly, we had this paper from Alan Goldstein's group in PNAS, and the title was Biogenic Carbon and Anthropogenic Pollutants Combine to Form a Cooling Haze Over the Southeastern US. And I want to talk about this figure in detail. So this is figure 1 from that paper. And what they're showing here is annual average aerosol optical thickness measured from outer space over the continental US. The hotter the color, the higher the aerosol optical thickness. And what they're showing here in B and C is the summertime increment. So it's the summertime aerosol optical thickness for June, July, and August. And subtracted from that is the aerosol optical thickness from December, January, February. And so this is showing the summertime increment from MISR and the summertime increment from MODIS. And then what they're showing here is a time series for that time period. The x-axis is year, the y-axis is aerosol optical thickness. The up and down lines are the MODIS and MISR measurements, and superimposed are these dots from the AirNet station at Walker Branch. And so this was a strong motivating factor. So we wanted to be in these red spots when we designed the SOAS campaign. And so SOAS is going on. I'm sitting in my shed reading papers that come out. And this paper came out by Bonnie Ford and Colette Heald. And they said the seasonality over the Southeast US in aerosol optical thickness cannot be caused by surface organic mass. And it cannot be explained by water uptake. And so Colette was an author on that Goldstein paper, and so it was very surprising to see this. And I was sitting there in the shed, all the airplanes are flying around, and I was thinking, this is terribly inconvenient. So what she's showing here is these stacked bars. The red is sulfate, green is organic carbon, so it's the AMS colors. And she's trying to find this seasonality in organic mass that they think they see from the satellites. And so she separates it out into 2 different surface networks, the search network and the improved network. She separates it out by urban and rural pairs. And no matter what, the green section is the same every season. And so she says, it cannot be. And so I thought, okay, that's very inconvenient. And so I took that analysis and I expanded it to the whole US. And so each dot here is an improved location. And I defined the time period from 2000 to 2007, same as in the Goldstein paper. And I looked at the summer minus the winter increment, and I tried to use the same exact color scale. And I see that the summertime increment in organic aerosol is actually highest in the Western United States. And I think that that's a consequence of fires. Fires in the Western US peak in the summer. In the Eastern US, fires tend to follow the agricultural cycle. And so they peak in the spring and in the fall, not in the summer. And so if I compare this geospatial pattern in seasonality with this geospatial pattern in seasonality, qualitatively they're dissimilar. And I agree with Colette that you cannot see this difference in the surface mass. So just a little bit of housekeeping. I'm going to start separating things out by areas of the US. So all the improved sites here, I'm going to call the Northeast. All of these I'm going to call the Southeast. These are the Midwest, Central, Mountain West, West Pacific. And I've separated out these geographic regions by the regional planning organizations responsible for air quality planning. Okay, so what I'm showing in this plot is a time series of that seasonal cycle in organic aerosol separated by those regions. So the x-axis in each plot is year, and the y-axis is organic mass concentration, the median, and then the interquartile range around that. And what we see is that there's organic aerosol variability all across the US, and in the Southeast, it's actually kind of the lowest. So I think the Goldstein group is really good. I think the Heald group is really good. And I was thinking to myself, there has to be a consistent story if I could just figure it out. So I went back and I reread the Goldstein paper. And it was the first time I've ever really read the methods section in a PNAS paper. And the font in that section is actually smaller. But So in this paper, the biogenic and anthropogenic emissions combined to form a cooling haze, they ruled out water uptake, but really they only looked at relative humidity. And then I read the Ford and Hill paper again, and they said the seasonal difference in water uptake, and in this case, they analyzed RH and aerosol extinction for a given particle composition was insufficient to describe the water uptake. And so I started to develop this hypothesis. I said, okay, well, aerosol water effectively scatters radiation in the visible part of the spectrum. And so those satellite measurements are seeing aerosol water if it's there, because they observe the particles unperturbed. And then I thought, okay, well, the routine surface networks that Colette is using, and most aerosol measurement techniques in general, drive water off. And so if there's aerosol water there, they don't see it. And then the other thing I thought is particle phase liquid water is a function of the particle concentration, the gas and particle chemical composition, temperature, and relative humidity. So if you only look at RH, you're not going to get the full story. So again, I took the data over the past 2 decades roughly, and I looked at relative humidity. And so I agree with Goldstein et al. There's hardly any variability in RH, especially if you look at the Mountain West or the West Pacific. There's certainly more variability in RH. But when we go back to that paper by Ford and Hill, there's not seasonality in organic aerosol, but there's seasonality in everything else. So there's this paper by Carlton and Turpin, and they say that in the eastern United States, aerosol liquid water is substantial, and it's controlled by sulfates. And sulfate is very high in the summer and very low in the winter. So here's a photograph of Great Smoky National Park in western North Carolina. And so this is what I was saying before. In the eastern US, when we have poor visibility, it's typically a consequence of an air mass having a high sulfate mass concentration and high relative humidity. So here would be a good visible range day, and here would be a poor visible range day. And so what is going on, and what I imagine the air parcels look like, is there's always some sulfate mass. The power plants never ever turn off, and the relative humidity is a little bit lower on this day. And on this day, the sulfate mass concentration is higher, the relative humidity is very high, and so there's a lot of aerosol water obscuring our vision. And so what we did is we took all of the improved data for sulfate, nitrate, and ammonium, and all of the meteorology inputs of relative humidity and temperature from the NARR. Not all of the improved sites have MET measurements, and we wanted to be consistent, so we used the NARR. We ran ISORROPIA. It's an inorganic aerosol thermodynamic model developed by Thanos Nennis. ISORROPIA is a Greek word for equilibrium. And then we looked at predictions of aerosol water mass predictions. This model assumes a metastable state, and during SOAS, we found that that was true. I don't want to get too stuck in the weeds on this, but these are comparing ISORROPIA to our quasi-direct measurements of aerosol liquid water during SOAS. We ran ISORROPIA in a box model mode with actual measurements. So the x-axis is time, and then the y-axis is mass concentration. The empty boxes are the ISORROPIA predictions, and then the blue boxes are our measurements. And so we think that ISORROPIA provides a lower bound, so there's some disagreement here, and if you want to talk about it offline, we can. But in general, it gets the pattern right, it's not completely out to lunch, and we think it provides a lower bound estimate for the amount of aerosol liquid water that's there. And then in addition to this, we applied the ISORROPIA model to the search site that we actually conducted SOAS at. So this x-axis is years, the y-axis is water mass concentration, and if we apply this trend, our SOAS measurements are pretty consistent. So we have a good feeling that this approach is reasonable. So we calculated seasonal differences in aerosol water for those improved sites for the same exact time period, and again, we use the same color scale as in the Goldstein. And this geospatial pattern looks a lot like the satellite pattern. So something that was interesting to us is Miser predicts this gradient over Florida, and even MODIS does a little bit too. And our surface mass estimates of aerosol liquid water also provide a gradient across Florida. And so qualitatively, we're thinking this aerosol water pattern at the surface matches the satellite observations. When we look at a time series of aerosol water over the past couple decades, separated by these regions, we see in these dry areas not much of a trend, not much of a seasonality. But in the eastern US, we see a lot. And this is the exact time period that they analyzed in the Goldstein paper. So if I compare our estimates of aerosol liquid water in the southeast with these AOT measurements, you kind of get the same pattern. And the thing that's really interesting to me is I work with a bunch of meteorologists, and they tell me all the time how chemistry is not important. They think physics is everything. But I try to remind them we make the freshmen take both because they're both important. And so that aerosol optical thickness is determined by the size of the particle, but the size of the particle is being determined by the chemistry. So I showed you before time series trends in relative humidity. And in the eastern US, remember it was pretty flat. And in the northeast it was pretty flat. And in the West Pacific and the mountains in the West, there's actually a lot of variability. And it's the opposite when we look at the sum of inorganic species that play a large role on particle hygroscopicity. So I'm showing here the sum of sulfate and nitrate. And there's a lot of seasonal variability in the southeast US. So we've been doing this for all the improved sites over the past couple of decades. Each dot is a location of an improved site, and the hotter the color, the more the liquid water that's there in the aerosol phase. So this section of the US always has some color, and this section of the US is always blue. We see interannual differences based on meteorology, and it's interesting to me when things start to pop up in North Dakota, maybe reflecting some energy choices we're making. And when we calculate the extinction coefficients for the aerosols that we're measuring at the surface, we see lots of seasonality in the eastern US. And it's not that we don't see any in the western US, but it's just a lot less. So I want to do an east-west rap battle. Okay, so for relative humidity, we see hardly any variability in the southeast US. We see a lot in the Mountain West. When we look at inorganics, we see a little bit of variability in the Mountain West, a lot in the southeast US. And the thing that's really interesting is the relative humidity and the particle hygroscopicity in the western US are almost perfectly out of phase. And so you get an aerosol water profile that's very flat. But in the eastern US, you don't. And that corresponds to this difference in seasonal aerosol extinction. Mm-hmm.
What are the differences in the particle size between the western and eastern?
So that's a really great question, because the particle size distributions that we have are dry, and they're not different. But if you were to add the water, you get this, I think, is an indication of how the particle size distribution is actually different, because we calculated the extinction coefficient with water uptake. Does that make sense?
How big are they?
With the water on them? I don't know. I'd have to, I guess you could calculate that, right? But you, like, use the growth factor that we get and do a size distribution like that.
I'm just thinking it will make a difference. The particle size will make a difference between the retrievals you get from the satellite.
Right. That's exactly right. And so this extinction coefficient that we calculate has a growth factor component based on the chemical composition. It's the improve algorithm. But yeah, I think that's exactly what's happening. I think that these particles are bigger, and I think they're bigger because there's water. But when you do the dry size distribution comparisons, they're very similar. But I think that's exactly what's going on. So this idea that I've been working on about how biogenic SOA could be enhanced by anthropogenic pollution, if sulfate and nitrate are controlling the amount of aerosol liquid water, then that's another anthropogenic modulation of biogenic SOA that's not typically accounted for. And so I'm starting to think that this might actually be happening. So in the southeast US, there was a paper by Blanchard et al. In 2013. And what he said there was how organic carbon in the southeast has been going down over time. And that's really intriguing, because most organic carbon particles in the southeast US are modern, suggesting a biogenic source like plants and trees. And there hasn't been regulations focused on controlling organic PM. And we think that water might be driving this decrease in organic carbon. So we calculated water at those same exact sites over the time period. This is our uncertainty, so we know there really is a decrease in water. And all I want you to take away from this table is that when we look at trends over the past decade in organic carbon versus water, it has the highest R squared, and it seems to be statistically significant. And so what that says to me is that the Clean Air Act is actually more successful than it gets credit for. So last year, I wrote a blog for EPA. It was a Valentine to the Clean Air Act. And the title was All You Need Is Love, but a little clean air doesn't hurt. And this was actually maybe the hardest thing I ever wrote. I kept talking to the communications people at EPA, and they hated it. And it was hard. I think I'm a regular human, but maybe not sometimes. So the x-axis here is year, and then the y-axis is mass concentration, and then the hearts are the monthly average in PM 2.5. Okay. So we've seen figures like this from Jose Jimenez's group, and they're convincing us that organic constituents are ubiquitous and dominant components of atmospheric aerosol all over the world, right? They show us pie charts, and this green part is organic aerosol. And so what I'm hoping to convince people of is that water is a ubiquitous and abundant part of atmospheric aerosol. So Jose is amazing, right? And he makes all his data freely available. And so when you have a good idea, you don't hide it from people, you beat them over the head with it, right? And so he beats us over the head with this. And so I took all of his AMS data and added this new component in its water. And it's really, really interesting because this time period in New York City was actually winter. And the relative humidity was lower than it is in Manaus. But there's double the amount of aerosol liquid water in New York City than there is in Manaus. Isn't that interesting? And it's totally due to chemistry, because the relative humidity in Manaus was much higher than it was in New York City for those two campaigns. Okay, so if I've convinced you of anything, I hope it's that aerosol liquid water is ubiquitous. I hope I've convinced you that the geospatial pattern in surface organic aerosol is at least qualitatively dissimilar to the aerosol optical thickness measurements, and that the aerosol liquid water pattern is qualitatively similar to the satellite retrievals. And the seasonality in aerosol liquid water is modulated by chemistry and not relative humidity. And right now, the next step that we're doing is we're doing QA on the extinction coefficients that I calculated at improved sites that are co-located with nephelometers. So I read Uli Poshel's science paper when they went to the Amazon and they were looking for organic aerosol and secondary organic aerosol. And they looked as hard as anyone in the world can look, and they actually didn't find that much. So their hourly max of organic aerosol was less than 1 microgram per cubic meter. But when I apply an EC tracer method to the Southeast US, I get a daily average of SOA that's 2 to 3 times their hourly max. And when I first read that paper, I thought it was, because they don't have NOx emissions. It's because they don't have sulfur pollution. And then I reread this paper by Liao and Seinfeld, and this is global predictions of aerosol liquid water in this plot. And there's a lot of aerosol liquid water over the Southeast, and they don't predict any over the Amazon. So that contrast with the Southeast US and the Amazon is something I'm really interested in, and hopefully you are too. So we proposed a session at AGU, interactions between biogenic and anthropogenic emissions, contrasting the Southeast US, Amazonia, and other regions. And so vote with your abstracts and vote for this. Thank you. I did none of this work by myself. It's not hyperbole. Thank you to NCAR for having me. Improve, search, NARR. Thanos makes his model completely free to the community. Literally hundreds of people have helped you every time you use these things. And Jose makes this data. And this is our funding, and thank you so much. Any questions? Christine?
Why is water going down in the Southeast?
Yeah, because sulfates is going down. Yeah. So cleaner act is more successful. For Sasha?
You compared mostly surface measurements.
Yeah.
Of course,
Yeah.
some especially things are moving up and down.
Yeah.
Within half an hour, up to the top of the boundary layer with colder and the humidity is approaching 100%.
So
Presumably particles are growing when they go up and shrinking when they go down.
yeah. So we've done calculations where we've extracted the boundary layer height from the NARR and then done the vertical profiles of those calculations. And so I could show you that. It's just too much for this.
I imagine it's still proportional.
That's exactly right. That's exactly right. Because the relative humidity goes up while you, and so it's the same thing but kind of more pronounced.
And just following up, so you say the water vapor goes down because the sulfate goes down.
Not the water vapor, the condensed phase liquid water.
Because, and what is the, I don't, maybe I don't know what the vapor is.
So sulfate and nitrate are chemical species that make particles hygroscopic, so they're more likely to take up water. And sulfate has been going down due to cleaner act rules and coal power plants and low sulfur geyser rules. And actually, that's what this big drop is here, is the low sulfur geyser rules in 2007. Christine? No.
Can you go back to the central and the Midwest?
Yeah.
What was, no, go right there. So what was going on in early 2000s? No, next one. In like central US around
Yeah,
2002, what happened there?
when
And there was a jump in one of the Midwest graphs as well at that time.
Yeah. So let's go back to
That one.
yeah. So all right. So this is a little bit speculation, but I think part of what I think is going on is NOx trading, and so there were time periods for which the NOx trading price dropped, and it became cheaper for people to just turn off their control equipment and buy NOx credits. And so there's time periods actually in Western Pennsylvania where there's one plant turns off its NOx controls, and then that emits more NOx than all the point sources in New Jersey. And so I think this is when the trading started happening, and so the cap wasn't high enough, is what some people would say, maybe not everyone. Uh-huh.
So do we expect the temperatures to start going up again?
Yeah, and there's evidence for that. There's it's not Nature, but it's like one of the daughter journals of Nature, and they're saying that the southeast warming hole is going away, and that it's been going away over the last 10 years. And that's consistent with our water hypothesis, and it's consistent with the paper by Alexis Atwood showing that visibility in the southeast has been getting better. Okay.
Thanks, Annmarie.
Oh, Shannon, hi.
I love that you extended the analysis to
Oh,
the
yeah.
western part of the U.S. I was curious when you were doing the analysis, if you considered including any other species that might be more relevant.
Yeah, so, that's a really good point. And the reason why we settled on that limited number of species is because we wanted to be consistent across all the improved sites. And so you're right, there's other species that would impact particle hygroscopicity, but we don't have measurements of them everywhere. And so, but that, doing that analysis for like a subregion where you do those measurements would be really helpful, I think. And that was the other reason why we used the NARR, because not all of the meteorology measurements are the same at all the sites. Uh-huh.
Yeah, I think I was probably going to ask the same question. So, are the organics responding to the water, or are they influencing the hygroscopicity themselves?
Yeah, so that's a really good question, and I'm going to say I don't know as well as I can. So that's what I think is going on right here is the organic fraction, not the organic mass, but the organic fraction of the aerosol was highest during this time period when we have the biggest gap in our water predictions and the SMPS measurements. And so that would suggest that organics, at least at that time of the day, are increasing particle hygroscopicity. But it happens both ways, because then when there's more water, then you can get more water-soluble carbon in. So it's, I can't speculate with sufficient confidence, but it seems like there certainly is an impact, and at least at this time of day, it seems like it is increasing particle hygroscopicity. Sure.
Related to the size distribution stuff, but I'm sure the other one that is uptake also going to pushing aerosols onto biogenic.
Wait, well, what?
Do you think this could be relevant to the health impact of the air? Like water uptake on this?
Yeah.
Like, could it be,
Yeah.
like, and could you be in a situation?
It sounds like you're reviewing one of my proposals right now. Yeah, yeah. Yeah. Yeah, I mean, there are some health studies that find a statistically robust association between negative health outcomes and sulfate. And there are some studies that do not. And when I make a spatial plot of what I think aerosol liquid water looks like, in areas where they do find a statistically robust association, there's lots of aerosol water. And in places where they don't, like Santa Clara or Phoenix, there's no aerosol water. So I think part of what's happening is a polar species, which organic polar species have been shown to cause inflammation. Those species that like aerosol water, why wouldn't they like the water in my body? And so I think that sulfate is sometimes a surrogate for those other species, but not always.
Just I think also Scott was asking, does it change the size distribution so that you're going above 2.5 as well?
Yeah, right. And then the relative humidity in your body is very high.
I mean, like, it's changing, like, are you now in the coarse mode, or are you still staying pretty small, under 2 microns?
Yeah, I don't think you're getting into the coarse mode, but yeah, I don't think so.
So it's not a protective effect then by making larger animals?
No, I don't think so. Yeah, no. But that's a nice thought. I like that thought. Yeah, it could, right? But the way that we typically measure size distributions, we dry the aerosol, and they're perturbed and not in their natural state. All right, go get the tree limbs off your houses and fences and. Yeah.
Do we abandon the anchor-type partitioning for liquid aerosols because of more flow-type partitioning, or what? Or do we have models that can span the full spectrum of?
Wow. Okay, circle of trust. I think the Odin model, we've been using it for like 20 plus years, and it's not working, right? It's like, well, yeah. Okay, so have you been to Caltech? It's really dry, right? And so they're thinking about this dry partitioning pathway a lot. And where I live, it's always humid, right? You saw the relative humidity in the eastern U.S. And so I'm thinking about water. I think that those processes do happen. My preference, that the framework that we put in models is an engineering approach to chemistry, right? And we don't have to do it that way anymore, I don't think, right? Like Gecko or something. Yeah, we have more computer time, right? And so we don't have to make those simplifications that were necessary 20 years ago. Computationally, I don't think we need to as much anymore. So I think, yeah, I think that that's right, going towards a more complex way. Yeah.
Okay, so I was using this microphone because we're recording it, and sometimes it makes it easier if somebody watches it to hear the question. But anyway, let's thank our speaker again. And there is a reception right now in FL0. So everybody, please feel free to come and join us.